Hi there, Space Nuts again, Andrew Dunkley here. This is a Q&A episode where we let the audience set the agenda. And today we'll be answering questions about the size of Jupiter. That's a why question. Another maybe what if question or why question is gravity finite? And what would the night sky have been like if you're standing on the surfaces of Earth in its very early era? Plus the demise of comets, can we generate solar power at night, and the acceleration of the universe. All our questions will be answered on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Just can't get enough of audience questions. It is Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. Yes, I do enjoy the audience questions because it tells me we've got an audience, which is amazing.
And we get a lot of questions in audio and text format, and we might as well go straight to our first one. And this one comes from David. Yeah, Dave in Inverell in northern New South Wales. Inverell, the gem capital of New South Wales. I would suggest a lot of people go up there fossicking for gems. And Dave, thanks for your kind words. Of course, in a recent episode, I went public about my fight with prostate cancer, and Dave has been dealing with his own issues. But Dave, I appreciate your thoughts. Thank you so much. Dave asks, g'day, Andrew and Fred. Just a quick question for Fred, because I wouldn't know the answer. Is that what you're saying, Dave? Why did Jupiter grow to such a massive size compared to other planets? Was there simply just more gas and material available in that part of the solar disk where it formed? Cheers, Dave. He might have answered it straight up, or is there something else in play here for it?
It's an interesting story, and I'm grateful to Dave for sending me down the rabbit hole of Jupiter's formation to see what the story is. I mean, it's what Dave says is partly the case. There's a big reservoir of gas and dust. I mean, we think it was the dusty material that formed the core, and then the gas was collected once that was in place. But there are some subtleties here, and I'm going to point Dave in particular to a very nice article. It's 6 years old now, 2018, on the Scientific American website. Really excellent website with very high degree of accuracy. But it's called "Why Was Jupiter's Rapid Growth Spurt Delayed for Millions of Years?" And it's basically saying that it wasn't just a continuous growing process that Jupiter underwent, but it actually was delayed, and the mechanism for that delay is quite interesting. So this is basically research that came from Switzerland. So we believe that the planetesimals, these sort of kilometer-sized asteroids, are what basically was the raw material of the planets, and the planetesimals in turn had grown from dust sticking together, partly electrostatically in the beginning, but eventually by gravity, and they formed their own gravity pulls in more stuff. So you've got these planetesimals, and the thinking is that during the first 2 million years of Jupiter's formation, it was in the right place for a lot of these things to smash into the proto-Jupiter, and that made it hot. A lot of energy caused by collision. And what that does is stops the process of gas accreting. In other words, the gas molecules that are out and about in space, which are eventually going to form part of Jupiter's very thick atmosphere that make it the big world that it is. These authors are suggesting that the bombardment by planetesimals gave so much heat energy that the gas did not want to collect. It didn't accrete. And so the planet grew more slowly than it had been. And then it says, the theory says that basically for the first few million years, within the first few million years, it was 20 times the mass of Earth. But then the larger planetesimals were bombarding it, and they, as I've just said, crashed into Jupiter, releasing energy, stopping the collection of gas. And so its growth rate, they now think, had slowed down, so that by 3 million years of age, it was only 50 times the mass of the Earth, which means that it took 2 million years to grow 30 times the mass of the Earth. But then sort of something happened, and it's a process that the authors of this article are calling runaway gas accretion, where the gas actually collects and then that makes it more massive, and then more gas collects and it's more massive. And so it grew to its current roughly 300 times the mass of the Earth size that it is now. So this is
like a snowball rolling down a hill type of thing.
Yeah, that's a very nice analog. Yeah, that's right. It's, you can't stop it. It's going down the hill. It's gonna collect more and more snow.
Interesting.
So they think that once Jupiter started to become dominant, then it was a runaway effect, because the bigger it is, the more stuff it pulls in, and basically grows to its present size. It's an article that it's got a lot of complexity in it, but is one that's worth reading, Dave, if you're interested in why Jupiter got to be the size it is. Actually, the original paper was published in Nature Astronomy, but there's a nice Scientific American article, as I mentioned. Why was Jupiter's rapid growth spurt delayed for millions of years?
There you are, Dave. There is a good reason for it. Right place at the right time, although it took a long time.
Yeah, it came in fits and starts.
All right. Thanks, Dave. Great to hear from you.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Our next question comes from Dean in Redcliffe, and I wonder if Dean is a Dolphins fan, the Dolphins football team based in Redcliffe in Queensland, and they've just lost their coach to a team in Sydney, the South Sydney Rabbitohs. And guess what the National Rugby League's done as the first game of next year? The Dolphins versus the Rabbitohs. So I'm wondering how Dean will feel about that if he's a Dolphins fan. Let's hear Dean's question.
Hi, Fred and Andrew. This is Dean in Redcliffe in Queensland. I'm a retired architect and I've been a Space Nuts listener for a long time. Finally, I have got around to sending in a question. I had always understood that the effect of gravity was infinite, although negligible at great distances. However, I recently heard that it may be finite. This seems like a reasonable idea when I think about ocean waves here on Earth. Ocean waves will dissipate to zero over enough distance if the wind stops pushing them. Ripples from a pebble dropped in a still pond will also dissipate to zero. This may be due to surface tension and friction between water molecules, which is an inherent quality of the medium conducting the waves. Now to my question. Space-time is the medium that gravity distorts. Could it be that the stiffness of space-time eventually overcomes the diminishing gravity of a distant massive object so that its gravitational effect becomes zero rather than just negligible? So I'm on the right track. Would the particles and dark matter within space contribute to its stiffness and to the dissipation of gravity waves? Thanks for the podcast. Look forward to hearing your answer.
Thank you, Dean. Great question. Really good question.
It is. And yeah, I guess the answer is maybe. I mean, Dean's right. We've talked about the stiffness of space actually in one of the, we talked about it in one of the Fred's flippant facts, didn't we?
Yes.
I said space is flexible, but not very. It's Young's modulus, which is the measure of stiffness, which Dean would definitely be familiar with as an architect. The Young's modulus of space is 100 billion times that of steel. So it's very stiff indeed. But I'm not sure that stiffness would contribute to an attenuation of the gravitational force. We're kind of talking about two things. Gravity itself is the distortion of space. Gravitational waves, which we know travel at the speed of light, are basically vibrations in space. And you can imagine that gravitational waves would be attenuated to zero by the stiffness of space because of that Young's modulus. But gravity itself is an inverse square law, which says that it's infinite. If you sort of have a look online to see what people think about gravity being, whether it's infinite or not, there's some quite interesting aspects come out. One is that, gravitational waves aren't infinite because eventually they would reach the cosmic horizon, the microwave background radiation, which is moving away at the speed of light. And these things would, they're basically, the gravitational waves themselves would interact with that and maybe cancel out. I'm not quite sure. I didn't really follow the logic of that one. And someone else thought that because the Planck length is the length in matter below which the laws of physics don't apply, the Planck length would be something that would stop gravitational waves being infinite. We're talking about gravitational waves now, not gravity, because eventually you get vibrations that were less than the Planck length. That was the point about that. So a lot of stuff that seems to me to be going around in circles. But my take on it is still that as an inverse square law, gravitation, reaches an infinite distance. It's effectively zero. It asymptotically approaches zero. That means it gets nearer and nearer to being zero. Formally never reaches it, but it is, yes, it's an infinite force. So I don't know that dark energy and dark matter thrown into that mix really add anything to it. It's a great question, Brian. It's made me think about these things. Sorry, Andrew, go ahead.
So are we saying that they phase out? They just sort of fizzle?
Well, maybe gravitational waves do, and it might be because of that stiffness. But gravity itself doesn't. And that's
okay. Until it runs into something else, and it's also creating a gravity.
Yeah, they'll try it. Yes,
that they meet and.
Yeah.
And then did they just push against each other and create that Lagrange point?
As you know, they can cancel out because exactly as you said, that's how Lagrange points work. Yes.
Mm. Yeah, it's really interesting. And it adds more to the empty vessel that is our knowledge of gravity.
It is. We really don't understand gravity.
Yeah. We just know it's there. It's one of those... I suppose if someone ever figures it out, that's a Nobel Prize waiting to happen, isn't it?
Definitely. Well, it'll be when quantum gravity really comes of age, when we really understand quantum gravity, which we don't at the moment. So, yeah, that will be it.
Right. Thank you, Dean, and all the best. Thanks for your question. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson.
3, 2, 1.
Space Nuts.
We've got another text question, Fred, and this one comes from Daniel, who is in Adelaide. And he said, I've saved up a few quick fire questions I'm hoping you could answer, please. Yes, we'd be happy to do so. We'll knock them all off one at a time. Quick fire means you don't have to spend too much time on them, Fred. We know the universe's expansion has been accelerating for about the last 5 billion years. Given the night sky seems fairly full of stars to the naked eye today, what would it have looked like if you were standing on Earth when it formed? Would the night sky have been as bright as day, for example? That's his first question.
Yeah, the answer is no. Our vantage point, 4.6 billion years ago when the Earth was forming, would be similar to what it is today. Yes, galaxies are closer together, and they might be, a little bit brighter than we see them now. But I think it would still be a similar sky that we'd see. You've got to go back a lot further in time to be able to see a night sky as bright as day. And what that is still being able to see the flash of the Big Bang. At the moment, that flash of the Big Bang has been redshifted into microwaves, which is why we don't see a brilliant sky. But we would if our eyes were sensitive to microwaves, or if we were looking at the early universe, not long after it became transparent, then we'd see a very bright sky.
That just a totally unrelated question, but that just prompted in my mind a thought about animals and insects. Would they see the night sky completely differently to us?
That's what some of Marnie's work is about. She works on that sort of thing from the point of view of light pollution. Yes, they do. They're sensitive. Many of them are sensitive to different wavebands than what we are. And in fact, some insects need the night sky. Dung beetles work by aligning their direction of travel with the Milky Way. So, it's quite an extraordinary. Yeah, they do. Check it out.
Wow.
Yep.
Wow. So many one-liners I can't use now. Yes. Rats. Oh, that's fascinating. It's totally off the track in terms of the question, but amazing. So that's your first answer, Daniel. Your second question, when a comet passes a star, it gets its dust and ice blown off, but will that comet ever lose enough material to become nothing? Or does it add material back in back as it traverses space? Well, some of them actually just end up crashing into planets and the sun itself, which means they're adding to those things somewhat. But can they just be sort of, as I've used this word before, fizzled out over time?
Yeah, they can. And what you would be left with is basically a trail of dust, which is what we pass through when we see meteor streams. So there probably are comets that have eventually dissipated. I'm not sure that any that have been seen by humans and recognized as comets, I'm not sure that any of those have dissipated to being just trails of dust, but that's the end process. Because, comets are made of dust, which is sort of bonded together by ice, and the ice sublimes, it goes straight into a gas and gets blown away, and some of the dust is released, and eventually you're going to wind up just with a little pile of dust that will spread itself along the path of the comet's orbit.
Yeah, and the Earth passes through these dust trails from time to time, and we see those meteorites that appear in the night sky at certain times of the year.
Meteors. They're only meteors if you do their line.
And meteorites when they hit the ground, yeah.
Yeah, that's right. So we see that. It's all right, Andrew. It's part of my job. That's exactly right. We see the meteor showers, which are because we're passing through the dust trail from a comet.
And the last question from Daniel is, could you develop solar panels that work at night by collecting energy from other stars and or the reflected light from the moon?
Yeah, the amount of light we get from stars and the moon is very small compared with sunlight. And I mean, we do know we can create electricity from all of those objects, and we do it as soon as we take a photograph of the stars or the moon with a digital camera, because that's, the sensors in your phone or your camera are generating electricity, which you can then measure and detect. But it's not really useful amounts. And I think probably the physics of, silicon, which is one of the materials that does this, will probably limit how much electricity you could collect. You probably have fairly low efficiency. So I suspect lunar panels are something that we're not going to see much of in the near future. They might be developed eventually. Yeah.
Yes, I certainly know that my solar panels don't show a skerrick of electricity generation at night when we've got a big bright full moon, because I've looked.
Yeah.
So technology, technology is beyond us at the moment. But I will check again next time we've got a big moon, because
Yes, I would too.
I'm not in the same house now. I've got a different array, so maybe it's improved technology, but I doubt it. I really doubt it would do anything. Thank you, Daniel. I think that's all of your questions done. And our final question today comes from Chris, who is in Tasmania.
Hi, Fred and Andrew. This is Chris here from the Huon Valley in Tasmania. My question is that we know that the expansion of the universe is accelerating, but I was wondering if we're able to detect whether the rate of acceleration is constant or ever so slightly variable, and whether that might provide a clue as to the structure of what the universe is expanding in, as in the expansion hitting regions of different density of who knows what, causing the acceleration to temporarily slow or speed up. That's my question. Thanks for the show. Really enjoy it.
Thanks, Chris. The Huon Valley is a glorious part of the world if you like cold weather. But no, it's Tassie's wonderful. I've got some friends down there visiting at the moment, and I'm checking out all their photos on Facebook. Judy and I actually honeymooned in Tasmania. 38, nearly 38 years ago. Oh my gosh. No, it wouldn't be that long. Hang on. How old's Kyle? 38. No, it'll be 38 years ago. 37 years ago. I don't know. I can't add it up. 7 and 14. But 35 years ago. There you go. I find it.
Judy, what's he talking about, Judy?
Yeah, she just rolls her eyes whenever I try to figure these things out. Acceleration of the universe, speeding up, slowing down, stopping, being interrupted. What's the story? We can't see that, though, can we? We can't see beyond a certain limit when we observe the universe. We talk about the observable universe, and then there's the universe beyond that because we just can't see it. So we really don't know what's going on out there, do we?
No, that's right. The bit that we can't see, we don't. We guess it's more or less the same as it is here. But look, this question, and it's a great one from Chris, is right at the forefront of cosmology. Has the accelerated expansion of the universe changed over time, or is it constant? And the theory that's been most popular in the last 20 years has been that it is constant. In fact, we've added what's called Einstein's cosmological constant to the equations that describe that. So what it's saying is the acceleration, by constant, I mean, let me change my wording slightly. It's proportional to the volume of space. So the more space you have, the more acceleration you get, the more dark energy you have, and hence the more acceleration. Now, I think the current thinking is that there may be a change. It may not be something that's got this cosmological constant. It might have varied over the age of the universe. And that would perhaps help to illuminate what dark energy is, because that's the problem at the moment. We've no idea what it is. It's just something that makes the universe expand more rapidly. It is a springiness of space. That's a nice way to put it, probably. But it's not. So any change in the acceleration wouldn't necessarily, in fact, probably not at all, as Chris has conjectured, it wouldn't speak of the universe ploughing into an area of higher density, because it's the universe itself that we're talking about. It's not anything that it's in. It's just the universe, the content of space and time. Yeah. But yeah, if it can be shown that it has varied, and there are observations going on as we speak to try and determine that, if it can be shown that it's varied, then that might illuminate what dark energy is. And give us some better idea. Because at the moment, we haven't a clue. And it's not just space that hasn't a clue. Nobody has.
That's the $64,000 question, isn't it, really?
Indeed it is, yes. Yep.
Yeah, that's another Nobel Prize winner, probably, if
that's correct.
Figure that one out.
Yeah.
So, Chris, you're asking Nobel Prize winning questions.
Exactly. A lot of our listeners do, which is great. That shows we should be a Nobel Prize winning podcast, really, shouldn't we?
No. Well, they had the Australian Podcast Awards the other day. We didn't get nominated because we didn't even know it existed.
Sounds like space nuts, doesn't it? Yeah.
Yeah. We just carry on. We just do our jobs. You guys can have all the prizes. We'll just do our thing. Yeah.
Yeah. And take the listeners with us.
Yeah. Exactly right. Thank you, Chris. Great question, but pretty tricky one at this point in time. Maybe down the track when somebody's waving their prize in front of us in the form of a Nobel Prize, we'll know the answer to that one. And if you've got a question for us, go to our website and click on that little link at the top that's got AMA and send us your text audio question. And that way we'll do our level best to answer them for you. And that's about it. And have a bit of a browse around the website. Don't forget to join our social media followers on the Space Nuts Facebook page, Space Nuts on Instagram, or the supporters page, the Space Nuts podcast group Facebook page. That's where listeners get together and chat and compare their astronomical pictures, and they even tell a few terrible dad jokes. I don't know where they got that idea from, but it's a great little community if you want to join. There's a few thousand people involved in that now, which is quite incredible. And that's about it. Thank you, Fred. We will catch you again real soon.
Sounds good. Thank you, Andrew.
All right. Professor Fred Watson, astronomer at large, and Hugh in the studio, couldn't be with us today due to cosmological inconsistencies. And from me, Andrew Dunkley, thanks for your company. We'll see you on the next episode of Space Nuts. Bye for now.
Space Nuts. You've been listening to the Space Nuts podcast.
Complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.